of all, again, thank you so much for coming. Really appreciate it. And welcome to Nuclei's headquarters. Um, what we're trying to start today is a community of people to exchange ideas and knowledge for all of our benefits, for all the perspective of different companies and different people. We could probably all benefit from sharing knowledge more than what we do. And so the idea here is to launch what we call Nucleai Academy. And this is to cross-pollinate and encourage an ecosystem in data science in general, in AI, and our particular niche is AI in medicine. And so our first series is going to be called Challenges in AI for Medicine. I should probably start off by just telling you who I am. So my name is Noah, and I'm a dad to these guys, and I did my PhD on these guys, these neurons, and now we're working on these guys. So at Nucleai, basically the entry point to a cancer diagnosis starts with a biopsy. Yeah, you get a sample taken, it gets sent to a lab, it gets stained, it gets scanned, and from there on, everything that happens in your treatment and your diagnosis tends to remain relatively qualitative. Meaning a pathologist will say, yes, okay, that is a cancer, it's this grade, it's that stage, and give you maybe some general things about it. But there's nothing quantitative about it. And our goal at Nuclei is to process these kind of images using computer vision and then downstream be able to produce quantitative measurements. For example, like the density of this kind of cell in this area and so on and so forth. And so that's what I do here. I aid in that effort. And oftentimes we then search for clinical relations between these spatial features or the distribution of these cells with some kind of clinical outcome. Yeah, so we look at things like clinical trials and maybe some kind of a target like the progression-free survival and the distribution of some cell type in cancer in some tumor. The size of the tumors, various metrics like that. And this talk that I'm giving today is going to be a little bit more general than the topic of just AI in medicine. And instead, what I hope to do is cover some of the truisms, the kind of things that we say but have difficulty rigorously explaining, trying to give a little bit of a background. And I'll already ask your forgiveness because, of course, in 45 minutes, you can't cover a year-long course in statistics, so I'm going to have to be a little bit shallow in some parts. And so, yeah, forgive me in advance. So I have to make another small apology. The title of the talk was originally Trading Bias and Variance in Small Samples. And I realized as I was creating this that just going through the definitions and getting to the point where you could actually start talking about this trade-off, you ended up in kind of deeper waters. And you started asking just general questions, things that we always say, like, oh, well, if you want me to succeed in this, I'm going to need many, many more examples. I need many, many more samples in order to do it. And we all kind of have an intuition that it's true. And oftentimes we can explain this intuition, but we don't actually have a rigorous way of saying, well, why do we actually even want more examples, right? Why is that actually true, that more samples help us? And so when answering that question and making all our definitions, I'm going to touch upon the bias-variance trade-off issue. But the idea here is to talk about actually why more data actually helps from a rigorous statistical point of view. One very interesting topic, which I'm not going to touch upon, is the trade-off between quantity and quality. You could imagine a case where you have a set of annotations where there's some kind of disagreement. There's noise in the label itself, right? And you could ask yourself, well, I could bring more labelers to label the same data so I get more and more agreement, or my ground truth improves in quality. Or I could keep the same level of noise and just increase my samples, right? And the question of which is better and what's the right trade-off, that's a really interesting question that I'm not going to talk about at all. So I just wanted to make clear that when I talk about more data, I'm talking about data that is similar to the structure of the data that we have. So it's, it follows the general, the rule that our data looks like, the data in the world. So we all complain about not having enough data. I mean, I don't know about you guys specifically, but I do. In every company I ever worked on, I've heard the complaint, and I've said the complaint myself, that I just need more data in order to succeed. What do you mean, 100 samples? What am I going to do with that? Yeah. But what your boss hears when you say that is annotations are expensive. They're going to take me time to acquire. Time is money. Just see what you can do with what you have, right? And that kind of makes sense because when you're pressed, when your back is to the wall, we all kind of know that more data doesn't guarantee a more impactful result, right? So if you give me more data, I can't guarantee you, because the whole hypothesis, what I'm trying to check, is essentially whether there is a connection between the set of features that I have and some kind of reality, whether it's this cancer or that cancer, or whether it's a girl or a boy, or whether it's whatever we're trying to classify. That's our hypothesis, that there's a connection between the features that I'm measuring and this outcome. If I knew that there was definitely a strong connection, okay, but the whole point of the exercise is we're not sure of the strength of the connection, right? So when pressed, they say, okay, I could give you an extra 1,000 examples. That's going to cost me this much, but you can't even guarantee that it's going to help you solve the problem. So that's one thing. And the second issue with always getting more examples is that we might be able to distinguish smaller and smaller differences, but as the differences get smaller and smaller, their impact is also smaller and smaller. So imagine, just for an example, that you had two populations of people and you wanted to compare their heights. And you wanted to be able to say that the heights of population 1 is different than the heights of population 2. It could be with your 100 samples, you say, okay, well, I don't see any difference. And if you then go and collect another 1,000 samples or another 1,000,000 examples, you find, okay, there is definitely a difference between the group. In terms of their average height, there's a difference of 1 nanometer. And so for your boss's perspective, it's like, yeah, okay, but a 1 nanometer difference, that doesn't help me. So if you're looking for a response rate of a drug, you could collect another 1,000,000 examples, but then, okay, the difference in response rate is going to be a tiny fraction of the response rate itself. And then you say, okay, the more samples helped you find a significant result, but actually it was completely not impactful. And because we can't make those promises, oftentimes there's a tension between actually getting more samples. So first, I wanted to try to give meat to our intuition on why more samples is beneficial, okay? But to do that, and this is where I kind of realized that most of the lectures are going to end up getting stuck in some ways, is that we have to get some definitions out of the way so that we're speaking the same language. Everybody in data science, one of the beauties and detriments is that everybody's coming from a different domain. And so we have to, in the end, make some kind of straight line where we're all talking the same language. So I tried to narrow it down. What are the bare minimum things that I actually have to define in order to have a conversation? And the first is random variables, what we mean when we say that. The second is going to be estimators. So what do we mean when we're making this estimation? We're going to talk about what is a bias and unbiased estimator. And lastly, I'm going to touch quickly on the definition of the central limit theorem and why it plays a role in all of these things. Okay. So let's start off with random variables. For one, it's actually not a variable, right? It's actually a function. And what a random variable is basically a map between something that we can measure, the heights of people and whatever, and the probability of those events happening, right? We want to define some kind of function which relates some space of measurable events to something about the odds of those things happening, okay? And to do that, we're going to need to go through some definitions. So first, let's build a probability space. Okay, we're going to build it out of these 3 building blocks. Oh, by the way, I should mention, whenever I'm giving a lecture, somehow my knowledge of Greek letters goes right out, and I start calling by mistake in the middle, one letter or the other. So if you start getting confused, just like raise your hand. Wait, I think you meant sigma there, not omega. I do that all the time. I don't know what my thing is. So anyway, we're going to build it out of 3 blocks. Okay, the first block is basically is omega. So I got it right this time. Is is the set of all possible outcomes. Okay, and now this set we can define as ever we want. So for example, if we're talking about rolling 2 dice, as the case might be, then we might just say, okay, we're interested in the outcome of rolling a 5 and a 1 and everything else, right? We're not interested in any of the other cases. So that would be, for example, the little blue one. Or we could talk about all the possible outcomes that we're interested in as being those green ones there. Or we could talk about all the options of rolling 2 dice, and that would be the red omega there. We can define it as ever we want. So that's the first element to this equation. The second thing we need, now I have to say I'm adding some stipulations and constraints here, and that's to serve my ultimate goal of defining a random variable, which makes sense. And you'll see in a minute why we get there. So the first thing we need is that this omega is in something in sigma algebra. Okay, that's our first, and that the complement, so of all possible outcomes, is no outcome, and that's the null set. So the null set also has to be in sigma algebra. In a second, you're going to see why that's important. And the other thing we're going to say is if we add some outcome to sigma algebra, for example, rolling a 2, then we have to consider the complement of that, the conjugate of that as well. So if you're saying, if you have a dice, then you want to be able to say, if you have rolling 1 to 6, and you're including as one of your possible events 2, you have to also consider the possibility of not rolling a 2, right? Okay. The other little weird constraint here is that we're saying that the union of all possible events is also a set within sigma algebra. So, a chance of something happening or whatever, one of these somethings happenings has to be there. And that's exactly the reason, is because we also are defining this kind of probability, which is again some kind of function which takes us from some event A into a space of between 0 and 1 for any event that happens to be in sigma algebra. Okay? Feel free if I'm confusing or something's not clear, just you could stop me. Yeah. An event. Some event. Rolling a 3. Okay. We're also going to say that the probability of the null set is 0, and the probability of something at all happening, of all our possible outcomes, is going to be 1. And then I'm going to also add this constraint that the probability of the union of all possible events is going to be equal to the sum of the probabilities of all events. Okay. So in the end, when you integrate over the whole space, you get 1. Okay. So let's just build one. For example, just for our little example here, we can just say we have some omega, which is the set of the rolling dice 1 to 6. And in our sigma algebra, we have the null set and its complement omega. And we talk about rolling 2. And so if we include 2, we have to include its null, which is rolling everything else, right? That's just that's the building blocks of our probability space. Those are the constraints that we designed. And why did we design them? I'm not going to prove it here, but the reason we designed it is because in order to get a random variable that takes some space, some measurable sample space, and moves it to the real number space, what we want is that for any event that happens, a little omega here, so x of omega is in subspace, and that subspace is in R. Okay, and what I'm basically I'm guaranteed if all of these things are met is that a probability, the probability is then defined for one of those events. So if you have some omega that you measure, then you have a random, if you're using random variables and you've met all of these criteria, basically what it says is that you can assign a probability to that event having occurred. Okay. But this is the thing. That's a nice measure theoretic definition, but it doesn't make sense to most scientists. So for example, imagine we were trying to measure the distance between 2 points, P and Q, on the surface of a sphere, right? And we were just going to draw our hand in and pull out a value. Well, since there's an infinite number of possible distances between points PQ, we would expect that the probability of drawing a particular value is 0, right? But that doesn't sit well with us. It doesn't sit well because we all know as scientists, we do an experiment, we get a value, right? So if the chance of getting a particular value is 0, how is it that we're able to draw even a single value, right? It doesn't make any sense. So the best way I can give an intuition about this, well, at least the best way I thought of to give an intuition about this, is imagine you were to draw a sphere around this distance, right? Not actually the distance itself, but instead just ask the question, is my measurement within this sphere? Yeah, so just to give you an example, imagine we have now a sphere, and let's say we're measuring the heights of people. So this sphere is between 1 and 2 meters, okay? And I ask the question, is the measurement between 1 and 2 meters? If the answer is yes, so now my entire space is going to be that big sphere, and I'm going to draw now a smaller sphere within it, okay? And I'm just going to ask the same question. For example, this is heights between 1.3 and 1.7, and if my answer is yes, I'm going to draw yet another smaller sphere. Now I'm going to be between 1.4 and 1.6, and so on and so on and so on forth. And because there is a chance of drawing something within our sphere, basically we can dive down this rabbit hole of spheres and get to the point where whatever measurement we happen to be in, we're basically asking, is it within this sphere of measurement? Yeah, we tend to disregard the accuracy of our particular measurement, but it exists. And because of that, we're able to dive through this, these smaller and smaller spheres. But there's some caveats that the more accurate, the more particular your measurement is, the smaller and smaller the sphere is, and therefore the smaller and smaller also the odds of you drawing that number. And so that's the way to connect it, let's say, to some kind of intuition. That depends, by the way, this little sphere analogy, it depends on some qualities of this metric space, which I'm not really going to go into now because of lack of space. But like, for example, one of the big ones are called Polish metric spaces. Polish metric spaces are technically defined as the space of your parents' house because you don't visit enough. Because at least for me, my parents are, Polish, Jewish, and so Yeah, but no, actually, you don't really need to know anything about that. But my point is just that there are these kind of special qualities of metric spaces. I told you I'm a dad of 3. I have to make dad jokes. It's just included in the package. Sorry, guys. So now that we have these random variables, let's use them to make measurements. Okay. Imagine that we have this population distribution that we know nothing about, and we're going to draw from that distribution a random sample, which is a set of random variables. Okay. So when we draw one of these samples, we can calculate for each draw the mean. We're going to now calculate essentially what the sample mean is, right? Now, this sample mean is actually what's called a statistic, right? It tells you how it tells you the mean of the samples that you drew. But it could also be an estimator if we decide that we're going to use it in order to try to predict what the actual population mean is. Yeah. Now, this is a moment where I'm going to stop and talk about bias and variance because I'm now defining what this estimator is. So in this case, we defined a very simple estimator. We took the sample mean and we say we want it to be an estimate of the population mean, what the real true value is. Okay. As soon as we did that, we built from a statistic estimation, an estimator. Okay. So a quick word on estimators in general. You could imagine a very simple estimator, right? Just a line. Okay, and if you had dots that are green and stars, and you just basically wanted to build an estimator that said if you're above the line, you're a circle, and if you're below the line, you're a star. Well, this estimator doesn't capture the actual structure of your data. Okay, and what that means is that even if you had an infinite number of samples, you wouldn't eliminate all of the error, right? Because you can't capture this with a simple line. But you could say that the variance, because you're only trying to estimate now here 2 parameters, is relatively small. Okay, so we have a relatively small variance, but even when we take an infinite number of samples, we have a kind of leftover, besides the variance of our model, we have a leftover error, which is due to bias. On the other side of the spectrum, we can choose an n-degree polynomial, right, which has n parameters. And so we have a very, very high variance because now we're estimating lots and lots of different points, lots of different parameters. And we can capture very nicely the structure. By the way, I'm not saying anything about generalization, note. But we can capture this structure very, very well. But we have a very high variance on our estimation. Yeah. So all these different parameters are going to have big confidence intervals. Another way to look at it is imagine you were throwing darts. Okay. And if I was wearing special glasses that made the bullseye look a little bit low, but I was actually really good at throwing darts, you can imagine that I would throw this case, right? So the bullseye is below where I see it, so I keep throwing. I'm throwing really well. All my darts end up more or less in the same place. That would be a case where I have a bias. I've missed my target by a set amount. On the other side of it, I could be not so great at throwing darts, but I do know how to aim. And so my darts kind of go all over the place, but if you were to look where they're centered on the bullseye. Yeah, so that people can see that I'm aiming for the bullseye. Yeah, so that would be a case where I have a lot of variance, but I have a relatively low bias. Okay, so that's basically all I'm going to say about bias and variance, in spite of the title. So that's actually not very helpful, right? Like it doesn't actually tell you that more samples are better so much in this case, right? But wait, here comes the central limit theorem. Okay. Central limit theorem in this case basically tells us that if you were to take an infinite number of samples, this sample mean estimation, if you look at the difference between it and the population mean, that distance is going to, you could draw that distance from a Gaussian that's centered on 0, which means as n approaches infinity, you're going to get closer and closer to a representation of your sample mean. That's what the central limit theorem and the weak law of large numbers basically guarantees us. But actually, that's still not so much help, because how the hell are you going to collect an infinite number of samples, right? I didn't tell you anything about what happens when n equals 100 or 1,000 or 1,000,000. It's great that at the limit it does something, but it doesn't really help us. Well, there's some side corollaries here. I could tell you that, first of all, the convergence towards the normal distribution is monotonically increasing with n. And actually, if you add a few constraints, bias-variance basically tells us that it's going to converge on the order of 1 over the square root of n. The other thing I can kind of tell you as a corollary, that things that involve the peak of your distribution are where there are a lot of samples. You need fewer samples to get close to the real values than you can say about the tails, which are by very definition rare. Okay, so we sought to answer why more samples are better, And the answer was a kind of obvious, well, the population means estimators' estimation approaches the true value as a function of sample size. But the problem is, that's great that we can better estimate the population mean the more samples we collect, but how does that relate to some performance of some arbitrary estimator, like a neural network or random forest or XGBoost or anything else? Well, first I should mention that this mean estimator, it's not the only one where this works for, right? Where the central limit theorem and the weak law of large numbers, all that stuff helps us. For example, I could design one like this, where I'm just trying to estimate pi. I have this pi estimator, where I throw dots randomly at here, and I count basically the ratio between the ones that land in the square and the ones that land in the circle. And as I throw more and more dots, this estimation is going to get closer and closer to pi, right? So there, I showed you, see, there's other estimators where it works for. But yeah, okay, fine. You caught me. These are kind of special cases. What I really want to know is, why is it true for my neural network? Why is it true for XGBoost? Why can I be so sure that it would be better to have more samples than fewer? Okay? So here's where we get to the gist of it. Well, the real difference is that for our neural network or a random forest or XGBoost or whatever we're training, we're more interested actually in the generalizability of our model on unseen random samples, right? We trained it on some training set, we have some test set, and we really want to know how well it's going to do on the test set. And so let's start off just by giving a very general definition of our error. Given some x, y inside a set of samples, right? Our error is just defined our error, we're going to say a couple things. Our error is going to be, we're going to say that this error is going to be drawn from some distribution, D, okay? And let's talk about now binary classification, because I think that just makes it simpler for us to have a conversation. And here's another little assumption that I'm going to say that's a little bit more dangerous. But I'm going to say, let's assume that our generalization, or the error on the unseen samples, is drawn from the same distribution, D, okay, as our training error. That assumption is actually part of a framework called the Probably Approximately Correct Framework, PAC. If you're unfamiliar with PAC, you should totally look it up, because it does give us some context about where things work and where they don't, and what assumptions you need to make it work, okay? But I can't spend too much time on it here. So it also comes with some other assumptions, like that you're independent and identically sorted, drawn from the distribution, and so on and so forth. But let's just say for now that you guys agree with the premise that the training error and the generalization error are drawn from the same distribution, any distribution for now. Okay, so the generalization error is simply if we define some model, some realization of a model, right? It's essentially a hypothesis which takes features as input, and then with those features produces a prediction, in this case 0, 1, and y being the truth of the matter, right? And so our error is simply how often we were wrong, divided by how many times we asked the question, m, okay? So what I said was that the distribution of this, the probability of this is drawn from the distribution, yeah, with an expected value of where we're wrong, places that we're wrong. Okay, so I'm gonna lean now on two little pieces of math. The first piece of math, it's actually, you might have recognized it from earlier where I used this equal sign. Here I'm being a little bit even more relaxed, where I'm saying the probability of the union of all possible events is at most the sum of probabilities of each event, okay? So I'm relaxing the condition a little bit. So I say the union of event 1, 2, 3, 4, all the way to k is going to be less than the addition of all their probabilities. Take that, we're going to put that aside. Okay, the second thing I want to talk about is what's called the Hofting inequality, and this means that the probability of getting an error greater than some value gamma, given a sample size m, is bounded by some expression, okay? So what it means is, if I were to draw now values zi to zm, these are our samples, and we're going to say these are random variables, and let's even say that they're drawn from the Bernoulli distribution with some expected value of phi, okay? So P of zi is equal to 1, we're going to call that phi. And zi is equal to 0 is going to be 1 minus phi. In that case, again, phi is just the average, right, or the rate. And so what I can tell you, and I'm not going to prove it here, but you can look up the proof, is that for a fixed gamma, the odds of getting a generalization error, the true error, the distance between the true error and our training error, greater than gamma, is less than some bound, which is 2 times the exponent of minus 2 gamma squared times m. You with me on that? Meaning the chances of getting an error bigger than gamma, or like that your training is misleading you compared to the actual error, greater than some gamma, is bounded. It can only be as great as this expression here. Okay? So notice that this expression, wait, let's make it a little bit simpler quickly. Let's just talk about now the case of a linear classifier, right? So a linear classifier, basically, we're just saying if the line, again, is greater than 0. And what is the act of fitting? This is another part of estimation. Our act of fitting is essentially looking for this linear expression which minimizes our training error. Yeah, that's the act of fitting a model. Okay, and actually that's called empirical risk minimization. That's what we're doing. Okay, so we can also extend this. So if we have H, which is some hypotheses, I could say that that's like an actualization of a model. So in the linear model, it's one particular linear model. If we wanted to find the best model, it's the one, again, that given a particular realization is the smallest training error. Okay, that could just as easily be for a neural net as a binary, or a linear classifier in our case. So I wanted to make the point that I wanted you to note earlier. I realized I failed to mention that expression that I showed you, that 2 times e to the minus 2 gamma squared m, is dependent on m. Right? And it gets smaller the bigger m gets. Okay? So it was just one thing to note there. So if we have a class of hypotheses, some neural network architecture, for example, and so all the realizations are in m, and let's say it's made up of a finite set of classifiers. So these classifiers in some ways are just mapping functions again, right? They're going to take some inputs and assign them some outputs, right? And so if we assume that x and y are drawn from D, okay, and again we define this as this z as us being wrong, misclassifying. So if x and y is drawn from D, then z is also drawn from D, okay? So now let's work on that a little bit. Our training error we define like this, okay? So this is basically the mean of m random variables zj, where zj is our misclassifications, right? All our misclassifications. And we could say these are drawn from this Bernoulli distribution, okay? And where our expected sample error, or training error, is basically this error here. This is the error of one particular realization of our model. Okay, so let's go back to this theorem here. Remember that I can make some guarantees as soon as that's true, right? I said here we're from a Bernoulli distribution. We meet all of these criterias. So now we can apply this nice little bound that we found. Okay, so our training error is this. And we know that you can't, using this Hofting inequality, we can just plug it in. The distance between our real error and our training error can be no greater than gamma. And the probability of getting such an error is less than this distribution, which is nice. It's great. That told us now that as m increased, for a particular realization of our model, we are dependent on m. Our chances of getting an error greater than some value goes down as m goes up. But, so basically, this is exactly what we said. The generalizability error approaches the training error as m increased. So in some ways, we've kind of half-answered the question. But wait, we're almost to the point now that we can say the more samples, the better overall, meaning for all the realizations of our model, okay? Because that was one particular realization, one value for m and b in our y equals mx plus b. So if you recall this little axiom that we said, the sum of all events, the union of all events is less than the sum of the probabilities of getting each event independently. So using that, what we can now do is we can plug in our event, right, is the difference between our training and tests being less than gamma, right? And we know that that's going to be less than the probability of the sums of all of these different hypotheses h all the way to k for a finite set of k's. I didn't say k couldn't be huge, but finite for now. Okay. So remember that we also have this little buddy here. And let's call this expression, just to make it easier to write about, delta. Okay? So let's now take the inverse of this little axiom that I showed you. Okay? So before I showed you that this had to be less than gamma, so basically the inverse would be there does not exist even one realization of our model such that the error between our train and test is greater than gamma. And that's the same thing as saying for all realizations of our model, there exists the difference between our train and our test error is less than or equal to gamma. You get that? Everyone with me on that? Cool. So if that's the case, then we're less than gamma, then this is going to be greater than 1 minus delta, right? Because we took the negation of our little axiom. Up to now? Great. So what do we find? We found now that for any realization of our model, no matter what model it happened to be in this case, that we can plug in this and do the algebra, I'll leave it to you, that m greater than a certain amount, right, greater than these expressions dependent on gamma and k models, is going to guarantee an error. So what does it mean? If we collect m samples, the probability of being more wrong than gamma is at most delta. Okay? Ta-da! More samples are better. Yeah? So next time I say, well, more samples might not help me, well, actually, it's not true. The more samples I have, the error I tell you will be more reliable, right? Because my training error and my test error will approach each other. Okay? And that's basically the whole message. So let me just take a moment and thank some of the people involved, and then I'll get to some questions. First, I'd like to thank Metal and Liat and more. They did all of this amazing organization, the food and the chairs and the media and all of this and the LinkedIn posts and everything, the registration, the RSVP. Thank you guys. You're amazing. Yuval and Yoav, thank you guys so much for consulting with me and helping me get through some of the math. And mostly thank you all for your attention. I really appreciate it. We really don't take it for granted that you came. Thank you.